Well, we've already reviewed the basic ideas of waves. Now it is time for the electromagnetic waves. This dates back to the 1860s when James Clerk Maxwell introduces his famous Maxwell's equations. These equations describe the electric and magnetic fields and their relationships. The first one says that the electric field is created by electric charges, and the electric field lines start at a positive charge and end at a negative charge. This second one says that there are no magnetic monopoles that we know of. This third one says that a varying magnetic field generates an electric field, and these electric field lines form loops. This last one says that a varying electric field or an electric current generate a magnetic field whose field lines form loops. Epsilon naught is the electric constant called the vacuum permittivity. Mu naught is the magnetic constant called the vacuum permeability. In the vacuum, they can be simplified as this, as there are no charges and no electric currents. So, in a vacuum, we have these two equations that say that a magnetic field that changes in time generates an electric field, and an electric field that changes in time generates a magnetic field. It's as if they feed each other back and forth. Just for fun,
You know there's always a reason other than just fun.
let's calculate the time derivative of the third equation. But because the partial of E with respect to time is the rotational of B from the fourth equation, we can write the curl of the curl as the divergence of the gradient of the magnetic field minus the Laplacian of the magnetic field. Because of the second equation, this first term is 0, so we get that the second derivative with respect to position is proportional to the second derivative with respect to time. This, as a matter of fact, is the wave equation, where the constant of proportionality mu naught times epsilon naught is 1 over the square of the speed of the wave. But if you calculate it, you find exactly the speed of light. I let you to find the wave equation for the electric field. Now, let's write a generic harmonic wave, electric wave, moving on the y direction as E naught times the sine of y minus vt k arrow. This electric field is pointing in the z direction. I'll also need a magnetic harmonic wave, B naught times the sine of y minus vt, this one pointing in the x-axis. I'm going to verify that these harmonic waves satisfy Maxwell's equations. First, I calculate the rotational or curl of the electric field. Now the time derivative of the magnetic field. Now the rotational of the magnetic field. And finally, the time derivative of the magnetic field. Now it's time to put all this together. Find that the conditions that have to be satisfied so that these harmonic waves satisfy Maxwell's equations is that E naught is equals to V B naught. Which together imply that V is plus or minus 1 over the square root of mu naught times epsilon naught. And the amplitude of the electric field is the magnitude of the magnetic field times the speed. Using now the result that the speed is the speed of light, which is 1 over the square root of mu naught epsilon naught, we get this simplified relation between the electric and magnetic amplitudes. Look that I have played with an electric wave moving in the y direction but pointing in the z direction, and also with a magnetic wave moving in the y direction but pointing in the x direction. So this electromagnetic wave is a transverse wave, which means that the oscillations are perpendicular to the direction of propagation. But also the electric field is perpendicular to the magnetic field. Or in Maxwell's words, light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. Also, we have found that at any point of the wave and at any instant of time, the electric field is c times the magnetic field, so they are always proportional. From our knowledge of the properties of the cross product, we can define E cross product B because E and B are perpendicular, the cross product is also perpendicular. So it will be pointing in the direction of propagation of the wave. So we define 1 over mu naught times E cross B as the pointing vector. From your courses in electricity and magnetism, you know that the energy density of the magnetic field is given by 1/2 of 1 over mu naught B squared. And the energy density of the electric field is 1/2 of epsilon naught E squared. That is a general result for electric and magnetic fields. And for the particular case of electromagnetic waves, we have that so they contribute the same to the energy density. Now, if we want to calculate the power transported by the wave over a cross-section area A, the energy per unit time, power is the energy over delta T. Energy is U, delta volume. Delta volume is area times the speed, delta T. So the power transported per unit area is UC. This we will refer with the letter S. With a bit of wibbly-wobbly math here, writing the energy density in terms of E and B, but this is the magnitude of the pointing vector. So the pointing vector is a vector that describes the power density of the electromagnetic waves and points in the direction of propagation of the wave. I know, there's a lot to digest here. Well, we'll continue later. Meanwhile, may science be with you.